of an electromagnetic wave, EM radiation, is light. And if it is a particle, what is the name of a light particle?
Photon.
So, as waves, they have, the features are wavelength and frequency. And the units of wavelength are going to be centimeters, angstroms, nanometers, any unit of length. The units of frequency are in seconds to the -1, sometimes called hertz. What they are is cycles per second. And units of energy are going to be either ergs, which we talked about, or joules. The formula, E is equal to H nu, or E is equal to HC over lambda. And why is that? Because what's nu? C over lambda, of course. Of course. So look out for the units, and that's the only possible complication that you can have. So tell me, what's going to be the energy? And let's do the EM spectrum just real quick. The visible. So you have an idea of the numbers, the range of the visible spectrum. So you have implanted, naturally implanted detectors for UV radiation right here. The information is input through this area, analyzed up here. And the ranges, and I'm going to put high energy over here. High energy, and this is going to be low energy. So tell me, the red or the purple, which one goes on the high? The purple, we talked about this. And the low energy end of the UV vis, it's got to be red. Okay? You had a question, I stopped you a minute ago. The little A with the little circle on top is angstroms. It's a unit. Angstroms. I'll tell you the conversion in a minute. The numbers for the wavelengths. The numbers for the wavelengths. Tell me, if I tell you the wavelength range, from 7 times 10 to the -5 to 4 times 10 to the -5 centimeters, which of those two numbers belongs to the purple? The long wavelengths or the short wavelengths? Short. Absolutely, because high energy, this is 4,000 angstroms, 4 times 10 to the -5 centimeters, or 400 nanometers. And this side, the longer wavelength is 800, let's put 700. 700 angstroms, 4 times 10, 4,000 angstroms. These are thousands. The angstroms are always in thousands, remember that. 4 times 10 to the -5 centimeters, and this is 700 nanometers. An angstrom is a very small unit of length, very small. So 1 meter has an equivalent in angstroms. So does 1 centimeter. An equivalence in angstroms. And this is how I want you to remember them. I want you to remember it this way. So that you never get confused. When you memorize conversion factors, there's a tendency of getting the numbers confused. Okay? The first thing to remember is that for the very high energy stuff, it's always going to have the shorter wavelength. We agree on that? Okay. The numbers are 4 and 7. That's the second thing you got to remember. That the numbers are 4 and 7, the edges. Now you pick one, whichever one you want to go with, because you can always convert to the other one. If you want to remember, times 10 to the -5, this is universal. Times 10 to the -5 centimeters in that area. So it's 4 times 10 to the -5 and 7 times 10 to the -5 when you're talking about centimeters. Everything else is a conversion. So now, the extra... Sorry. No, thanks. So, it's times 10 to the -5 when it's in centimeters. So pick one and remember it, because everything else is a conversion. Pick one and remember it. Remember the numbers are 4 and 7. The shorter version of the wavelength goes to the higher energies. Is that good? You think you can do that? Okay. So now everything else is a conversion. Now let's talk about conversions of angstroms. Here's how I want you to remember this. Angstroms are very small units. Very small. We good? Okay. So I think we can agree that if angstroms are teeny tiny units that are the lengths of cells and nanoparticles, because that's what we measure tiny things in, angstroms, right? So a meter stick is about how long? Like this? 39 inches? 3 inches more than a yard? About this big? So there should be a bunch of angstroms in 1 meter, shouldn't there? Right. Now, show me with your hands a centimeter. That's 100th of a meter, right? So do you agree that there should be less angstroms in here than there should be in here? Is that fair?
Yes.
Okay. The numbers are 8 and 10. So 1 meter has 10 to the 10 angstroms. Of course it should have 100 times more little guys in a meter than you have little guys in a centimeter. And that's how you remember that conversion. Okay? And then pick one, you know what the other one is. Alright, so here we go. What is, find the energy of a photon with a frequency of 2.33 times 10 to the 14 cycles per second. 10 to the 14 cycles per second. What are you going to do? Okay, but what formula are you using? How do you find energy given a frequency? That one. Energy is equal to h nu. And what's the value for h? We have it last time. What is it? H is equal to 6.63 times 10 to the minus 34 joules second, or 6.63 times 10 to the minus 7 erg second. And these are dots. They're not lines of division. They're multiplication dots. So what are you going to do? Just plug it in, your favorite. Your favorite. E is equal to, what was the frequency? 2.33 times 10 to the 14. And cycles per second, what is that? That's seconds to the minus 1. Those are the hertz, units of frequency. And what are you going to put for H? What are you going to put? You got two choices. Ergs or joules. Up to you, up to the problem. It's up to you. It's a matter of unit. What do you want to use? Doesn't matter to me. You want to do joules? Fine. 6.63 times 10 to the minus 34 joules dot seconds. Look at the unit cancellation. What's your unit of energy going to be? Joules, right? Watch this. That's seconds to the minus 1, right? So it cancels with the second. Of course you get joules. Because the units are internally consistent. So what do you got? What's the energy of that radiation? Energy equals? Guys, get a calculator.
1.54.
This is on the last lab exam. This is on lab exam number 3. It's just like this. Exactly. And on the last test and on the departmental final, this question is on every test from now on. So hurry up. 1 point? Everybody getting the same thing? 1 point?
Yes.
4?
5.
5, 4.
5. What's up to the 4?
4.
4.
Okay. Times 10 to the
10 to the negative 19.
minus?
19.
And the units are?
Joules.
We good? Okay. With this algebra, how about this? Find me the wave, one more. Find me the wavelength. Find me the wavelength of a radiation. The wavelength of a radiation that has 2.73 times 10 to the 16th seconds to the minus 1. Find the wavelength of a photon with a frequency of 2.73 times 10 to the, I said 16, right? 16. 16. Seconds to the minus 1. I should really use the symbol S. Seconds to the minus 1. Now what are you going to do? If I want the wavelength, what are you going to do? Well, what's new? Speed over lambda, of course. And what's the speed of light? What's the speed of light? 3 times 10 to, if I say 8, what is it?
Meters per second.
Meters per second. And if I say 3 times 10 to the 10, what is it?
Centimeters.
Centimeters per second. Because of course, there should be more of the little ones. There should be more of the little ones.
Does it matter?
So if they say find wavelength, what are your options? Depending on the units. Centimeters or meters. Those are your choices. And it's all about the units that you pick. So which one do you want to do? Meters or centimeters? Fine. So if you want to do it in centimeters, what are you going to put up here? 3 times 10 to the 10. Centimeters per second, right? Divided by lambda. And what did they tell me the frequency was? 2.73 times 10 to the 16 seconds to the minus 1. What are you going to do to get lambda? Don't get creative. That is on the bottom, so where does he have to go? To the top of the other side. X has to be alone, positive, and on top. You cannot solve for X if it's in the denominator, because you're finding the inverse, and that's not what you want. X has to be alone, if you can't have any coefficients. Positive, and on top, in a numerator. So if I put this up there, what has to happen with this number? It has to go to the bottom of the other side. So lambda equals the speed of light divided by the frequency. Survey said. What is it?
Come on. What is it?
1.11 times 10 to the negative 6.
How much?
1.11 times 10 to the negative 6.
And these are in units of?
Centimeters.
Centimeters. Did everybody get the same answer?
Yes.
Everybody got the same answer? Yeah? Okay. One final question. Can I see a radiation? Finish this sentence for me. Yes, comma, as long as its wavelength
It's high.
High.
as long as its wavelength is, be more specific, between 4 times 10 to the minus 5 and 7 times 10 to the minus 5 centimeters. Of course, that's how we started this discussion. What is it that's available to us to perceive in the visible range with our limitation with the EM detectors and all that? We good? So can you see that radiation? Can you see a radiation whose wavelength is 1 times 10 to the minus 6?
No.
No, it's too,
Low.
it's too small? How do you compare a thing that's times 10 to the minus 5 versus a thing that's times 10 to the minus 6? The thing that's times 10 to the minus 5 is too big. So this radiation has a wavelength that's too short. Yeah, when it comes to wavelength, don't say small, say short. because it's a unit of length. Wavelength, right? One last detail, wavelength. Everybody and their brother likes to do the distance between the waves from the top part of the wave and call this a wavelength. Every book does it. Please don't be confused, and please know that these waves are completely symmetrical. So any equal position in a wave is a wavelength. They choose to do the two tops, so why can't it be the two bottoms? Because it'd be the same measurement. Or hey, how about the two halfway ups? Because they're going to be the same measurement. The wavelength of a wave, an EM radiation wave, is the distance between two equal points in the wave. You want to pick the two tops? That's fine, but it doesn't have to be. Just because the waves are symmetrical. We good? Okay, so the picture of the atom and electromagnetic radiation. The picture of the atom and electromagnetic radiation. Electrons are found, according to Bohr's model of the atom, according to Harry Moseley's atomic number. The picture of the atom is such that there is a nucleus where the protons and the neutrons are, and everything else that's electrons are going to be in layers, in energy levels around the nucleus. And the definition of the level is the principal quantum number, symbolized by the letter N. It's called, has a name, it's called the principal quantum number, principal with an A-L, principal as in the main one. Principal quantum numbers, these are it, the main energy levels. So when we're filling electrons, you're actually filling them according to energy levels. The capacity for electrons in the energy levels, 1, 2, 3, 4, etc. Electron capacity is 2n squared. That's how many electrons fill each energy level. In each energy level. Take, for example, level number 2. What are the orbitals found in level 2? 2s and 2p. How many orbitals are in every s? Say 1. How many orbitals are in every p? Say 3. Good. 1, 2, 3. How many electrons fit in each orbital? 2. What's that called? It's got a name, a guy's name. The electron configuration is the whole thing. But not Aufbau, the other one. You remember Pauli's exclusion principle? Pauli's exclusion principle. Pauli's exclusion principle says that you can only put 2 in each one. What's the principle called for when you have to do one at a time before you double them up? Something with an H. Hund's rule. There you go. Hund's rule. That's Hund's rule. And what's the order? That's Aufbau. Aufbau is a German word that means build up from the bottom up. And there's no Mr. Aufbau. That's a trick question. That Mr. Pauli, well, Dr. Pauli, right? Dr. Pauli and Dr. Hund were people, but Aufbau, not a person. That's just a German word. All right, so how many electrons can you possibly shove into level 2? Say 8. Good. So a maximum of 8 electrons, right? So if n is equal to 2, and then you do that operation, what do you get? 2 times 4 is 8. Right, the capacity for each level. The capacity for electrons for each energy level is 2n squared. You can try it with anyone you want. Try it with a 3 that has a d orbital. In level 3, what do you got? 3s, which has how many lines? 1. How much is 3p? 3. And how much is 3d? Perfect. So how many electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18. Yeah? What's the capacity? 2n squared. So that's 2 times 3 squared, which is 18. Okay? So remember, the capacity for each level is 2n squared. Those electrons that we're going to locate in a minute and do all the electronic distribution, those electrons can move within the energy levels. They can actually move within the energy levels. Take an electron normally residing on the second floor of nature's electron apartment building. Normally resides in level 2. Wants to move up. Thing is that to move up is to move up into a higher energy level. The levels next to the nucleus have lower energy. These are the inner orbitals, closer to the nucleus, right? And these are the outer orbitals, away from the nucleus, higher energy. Why should it be so? Because the protons in the nucleus are positively charged, and they are in charge of what happens at a certain distance. The further you get from the nucleus, the less you feel the effect of the nucleus. Which is why the electrons that are in the outer fringes are the ones that get usually lost. That's how you get your ions. Gaining and losing in the valence shell out there somewhere. Because of that, they're the farthest one from the nucleus. The electrons that reside close to the nucleus are referred to as core electrons. It's really hard to rip those guys out. And where does radioactivity come from? Radioactivity comes from the nucleus. Radioactivity comes from the nucleus of the atom. It's a form of nuclear decay. Alpha, beta, and gamma radiation come from the nucleus. So this means that there are electrons coming out of the nucleus. Weird, right? That's true. Because once subatomic particles in the nucleus break apart, some of them emit electrons out of the nucleus, which is a crazy thing. It's a form of radioactivity. It's called beta radiation. Don't forget that. The radiation comes from the nucleus. So the story goes that electrons that are minding their own business, assigned their orbitals the way you know to assign them, 1s, 2s, 2p, 3p, whatever it is. They're minding their own business, and that is called the ground state. And in order for them to move up to a higher energy level, say for example that one, he would want to go from level 2 to level 4, from an inner level 2 to an outer level 4. And just like you need to pay for a plane ticket, this plane ticket is in the form of a difference in energy. That difference in energy is said to be quantized. Quantized, measured exactly, quantized. It means this, that you can't get a little energy and just make it halfway to the 3 and jump back. Every bit as much that you can buy a plane ticket, you don't have enough money to go all the way to New York City, and you just pay like half and offer the airline to jump off over Savannah. And same way that's not going to ever work, this doesn't work either. It's like throwing a light switch. You either have the energy to jump and make the complete jump to 4, or you are not going anywhere. That is called quantized. Okay? The energy required to jump between the levels is quantized. You either go or you don't. There's no halfway. Is that okay? Those are allowed transitions. Allowed transitions. Fun. So a transition occurs because somehow I got the energy to go from 2 to 4. So now I'm out here. Little star. Once I gain enough energy and I jump to a higher energy level, I am called an excited state. I swear to God, that's what it's called. Excited state. And at higher energy level. Particles, molecules, etc. that are elevated to a higher energy level are called the excited state. That's the official language. So far, there has been an absorption of radiation. A particle has absorbed a certain amount of radiation and jumped to a higher energy level. That's what's happened so far, correct? That's not nearly as interesting, the absorption, as what happens with the return. The way up is called absorption. The way down is an emission. Because whatever energy you gave it to go up, for the most part, you're going to get it back when he returns. Because whatever goes up must eventually come down. And that works with this too. Excited states return energy to the environment. And why is that interesting? Because sometimes I can see this energy. When can you see a radiation? As long as its wavelength is between 4,000 to 7,000 angstroms. That's right. The Chinese figured this out 5,000 years ago because they've always knew that if they took certain minerals and packed them with explosives, with ammonia and manure and stuff, and lit a fire to it, what do you get in the sky?
Fireworks.
Beautiful colors. They had figured this out a long time ago. They knew exactly which minerals to use to get a deep red, to get a blue, to get a green, to get a yellow. They knew this 5,000 years ago. This, coming soon to a 1045 lab near you. This is your last experiment. I thought, yeah, no, you're not blowing anything up, unfortunately, sadly. I know, I'm sorry, I know. You should be allowed to blow things up, I know. It's the lawyers, those damn lawyers, man. Well, and the parents get funny about missing limbs and things. Never. No fingers. I'm kidding, just in case. I'm kidding. Rydberg's equation. Rydberg's equation. For electronic transitions. If you ever wanted to know if you could see a transition between an inner and an outer level, Rydberg's equation will tell you. Rydberg's equation equals z squared times r times 1 over the inner squared minus 1 over the outer squared.
What?
And please remember it as soon as possible. I don't know what to tell you. Just try to remember it as soon as possible. You start out by remembering. Here's what you do. You start out by remembering that there's going to be, listen, just listen. You start out by remembering that this is always the inverse of the wavelength. Rydberg's equation is the inverse of the wavelength. So it's 1 over lambda. Z and R, I'm going to tell you what they are in a minute. But this, remember it's a fraction, right? So in the parentheses, it's going to be the subtraction of two fractions. So you remember this format first. This is the inner minus the outer. What do you think that means? Inner and the outer. That's the jump that you're looking for. So that's easy. 1 over the inner square minus 1 over the outer square. So the inner and the outer, that's all right. So what do you got left? Now you got left to remember, what the hell is that? That is the atomic number of the element that you're talking about. That's the atomic number of whatever element you're trying to analyze a jump for. And R is Rydberg's constant. It's 1.1 times 10 to the 5th centimeters to the minus 1. 1.1 times 10 to the 5th centimeters to the minus 1. Why should it be centimeters to the minus 1? Because it's 1 over lambda, so of course the centimeters are on the bottom. We good? So what do those problems sound like? Can you see a transition between levels 0.2 for an electron in a hydrogen atom. And these numbers are mad lib. These numbers are an absolute mad lib. Theoretical transition. So how are you going to answer this question? Can you see a transition? How are you going to answer it? As long as lambda is between what? 4,000? Between 4 and 7 times 10 to the minus 5. And where are you going to get that lambda? From here. So, fill it up. Your favorite. Get a calculator. This is important. Because this is how most people get it wrong. They stop after they find 1 over lambda. So let's all get together to the same number. Get that calculator. It's hydrogen. So that's atomic number 1 squared. Rydberg's equation has Rydberg's constant. 1.1 times 10 to the 5th centimeters to the minus 1. And 1 minus the inner squared minus 1 minus over the outer squared. Which was the inner? As a transition between 4 and 2, so which was the inner? So that's a 4. And the outer? And the outer? Is a 16, right? Just saying. We gotta pick up a little speed. Gotta pick up a little speed. 1 over lambda. Here's my suggestion. Here's my suggestion. That you don't work this out unless you're very good at the parentheses. Don't try to use them because you're going to get it wrong like 17 times in a row before you figure out what you did wrong with the stupid thing where you probably put the parentheses in the wrong place. So do yourself a favor. Just do this one first by itself. This is 0.25 minus whatever the hell that is.
1.6.
Do whatever you can do as fast as possible, but it has to be right. You work the way you work, but it's gotta be right. So my suggestion, do this number first, and then multiply by this, and this one nobody cares, because it's a 1. So now everybody do this, and tell me what this is equal to. I want to know what 1 over lambda is equal to, right now. Go, 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 go. 2 what? 20625. Okay, wait. But no points yet? No. 206 dot. Yeah, I think we got enough numbers because we were going with like 3 or 2 significant figures. We good so far? Okay, did everybody get the same answer? Don't clear the calculator, don't do anything. You have this number displayed, everyone? You got that number displayed? Get it. Get that number, get it displayed. Hurry up. Get it displayed. Did you get it? Okay, how many people got it already? Okay, find in your calculator the following key. X to the minus 1 or 1 over x. And press it. And hit it. What'd you get?
0.0004848.
4.84 times 10 to the minus 5. Did everybody get that?
Yeah.
Did everybody get that?
¿Cómo
Are you
agarro el
sure?
número de abajo? ¿Y agarro el de abajo?
Everybody got that?
¿Cómo agarro el de abajo?
I was before, I keep getting 9,166 on mine.
Open up each calculation. Open up each calculation.
Este es lo que te da.
And find out what each one of them is. Tell me what this is equal to. Alright, everybody, tell me what I want to know. How much is that parenthesis equal to? Just this. 0.1875. And that's it. 0.1875. Did you figure it out?
Yeah, I was mistyping something.
It takes practice. So make sure you get it. Make sure you get it right. Make sure you get it right. Did everybody get the same number?
Yeah.
Everybody get the same number? What are these units? What are these units? Centimeters. Can you see this radiation?
Probably, yeah.
Can you see this radiation? Why? Because it's between 4 and 7 times 10 to the minus 5. We okay? Any questions? Okay. Average atomic. Yes. I told you guys to find, once you have this number displayed, don't touch it, don't do anything, find one of these two keys on your calculator and press it. Because that's the inverse, and you don't have to do anything else other than just hit the inverse. It's the fastest way to get an inverse. The fastest way to get an inverse is to just hit that key when you have the other number displayed. Alright, let's go. Average atomic mass. Average atomic mass. Actually, you know what? Let's not do average atomic mass. We'll do average atomic mass on Monday. Electronic distribution. Electronic distribution. Alright. I'm assuming you already know how to do this. Let's assume you already know how to do this. So, if you don't remember, you're going to have a hard time catching up. So here we go. The electronic distribution is based on the Aufbau principle. It's based on the Aufbau principle. And it is the order in which you put electrons in the orbitals that are available. How do I know the orbitals that are available? I have to look at the atom on the periodic table. So in order to find the electrons that I'm actually filling in the orbitals with, which number do I look at? The larger value or the smaller value? The smaller value, because the smaller value is called what? The atomic number. And what is the two things that the atomic number represents?
Protons.
The protons in the nucleus and what else? The electrons in the neutral atom. So here we go. How many electrons does magnesium have? 12. How many electrons does carbon have? How many electrons does selenium have?
34.
How many electrons does strontium have? How many electrons does iron have? How many electrons does titanium have? Okay? Are we in agreement? So that's how I know how many electrons to fill in. We good? All right, let's try silicon. How many electrons do I fill in? 14. So I got 14 electrons for silicon, right? Okay. So what's the order then? What's the order? No, we gotta do the full one first before doing the noble gases. We gotta do the full one first. The noble gases we'll do later. What's the order? In which I put in? 1s, and then what?
2s.
And then what? And then what? And then what?
3p.
And then? Then? Where are you getting these? How do you know these? I never heard of 5G before. Never heard of that. 6S, 15, 6H? I don't know about that. No. 7S, 7P. But you know, if I ever get atoms that big, we're ready to put the numbers in. It's just like counting. Just because you're not using all the numbers all the time, don't mean they're not there. Just saying. 7F, and so on, and so on. Hell, as soon as we get a brand new period in the periodic table, the next number is an 8. I don't have one now, but that doesn't mean it's not there if I need it. Because if you have a house that has 25 rooms, you might not need them all at the same time. But you know they're there. The order is called the Aufbau principle. This is Aufbau. This is Aufbau. This is the shorthand for the periodic table. wanted to carry the periodic table in a little teeny tiny handwritten note, this is it. This is the periodic table. Here we go. What order is it that you said I was going to fill this in? First I fill what? First I fill what? The 1s. Okay. And then I fill what?
2s.
Who completely fills the 1s? Helium. And then what do I fill? The 2s. Who completely fills the 2s? Beryllium, because these are 2s1 and this is 2s2. So after the 1s, what comes? The 2s. And after the 2s, what comes? The 2p. And who completely fills the 2p? Neon. And tell me, after the 2p, what goes? The 3s. Of course it does. And after the 3s, what do you fill? The 3p. Of course you do. And after you finish with the 3p, what do you fill? Yes, you do. Yes, you do. After you fill in the 3p, where do you go? 4s. Yes, you do. And after the 4s, what do you fill? The 3d. And after the 3d, what do you fill? The 4p. And after the 4p, what do you fill? The 5s. And after the 5s, what do you fill? The 4d, the 5p, the 6s. And then finally 4s. This is the periodic table. And I will always know how to fill electrons according to the Aufbau principle. This is the periodic table. In arrows, so you know which one to fill first. And you never get lost. This is the periodic table. Do we understand the relationship between these two?
Yes.
Good. Hit it. 14 electrons for silicon. What do you got?
1s2, 2s2.
Here's the thing. Here's what I do. 14 electrons. 14 electrons. That's probably going to take me as far as what?
Neon.
Say 3p2. 3p2. So I probably need only up to 3p. Let me stop there. Was everybody able to follow that? If it's a no, you got to tell me. What's the electron distribution of chlorine? 3p5. What's the electron distribution of strontium? 5s2. What's the electron distribution of zinc? 3d10. 3d10. What's the electron distribution for phosphorus? 3p? 3, right? Does everybody know what I'm doing?
Yes.
Okay, perfect. So knowing that I'm going to go to silicon, I'm going to end up at where? 3p2, so that's about as far as I go. 1s, 2s, 2p, 3s, 3p, and away I go. Obeying the Aufbau principle, meaning I'm going to go first to the 1s, then the 2s, the 2p, then the 3s, and after the 3s I fill in the 3p. So 1, 2, 3, 4. Why am I doing arrows up and down? Those are the spins, right? So those are the spins. One up and one down, correct? And now, Hund's rule of maximum multiplicity, which means that up to here I've got 4, 5, 6, and 7, 8, 9, 10, and look, Ma, I'm at neon. 10. After 10, where do I go? 3s, and I'm at sodium. But I'm not done, because I got to get all the way to silicon with 14, right? So this is 11, 12, 13, and 14. That's the electronic distribution for silicon. We good? Okay. Do iron for me. 26 electrons. 26 electrons. What do you got? You know I can count these. I can. I can count these if I remember the exceptions. D1, D2, D3, D5 by exception, true D5, D6, D7, D8, D10 by exception, true D10. So if it's iron, D1, D2, D3, D5, D5, D6. So it's going to end up being a what D6? It's in period 4. It's a what D? 3, because the D's always lag 1 behind the count. And the S lag 2 behind the count. Okay. So 26 electrons. Here we go. 1s, 2s, every p orbital, set of orbitals has how many lines?
3.
3. And every d orbital has how many? 5. So after the 2p comes the 3s, and the 3ds, 1, 2, 3, 4, 5, and finally the 4s by himself. And this is how I set up my orbitals. I set them up in numerical order to make my life easier, because I'll always know how to fill them. I will always know how to fill them, because I've got the alpha principle, which is my periodic table. I will always know how to fill them. So I do not have to worry about burying the 4s inside of the 3D. People who do that get problems on the lab exams wrong, because they forget that when you make ions, you have to take them out in numerical order. I do my electrons in numerical order. I count 1, 2, 3, 4, 5, 6, 7. I do not count 1, 2, 3, 4, 3, 3, 4, 5. That's nuts. I do them in order to make sure I've got everything in there, and I fill them up according to the periodic table. I will always know how to fill them. The fact that I put this 4s where I put it does not affect my final answer. But to those of you who insist of burying the 4s inside of the 3D, you've got an 80% chance of getting a certain problem wrong when they ask you for ions. Because the ions, you have to take them out in numerical order. And if you do it my way, there's nothing to think about. You get them right automatically. How many electrons? 26. Here we go. What do I fill first? 1s. 2, after the 3, 4, 5, 6, 7, 8, 9, 10. Neon. 11, 12. 13, 14, 15, 16, 17, 18. I'm at argon. What do I fill after the 3p?
4s.
What do I fill after the 3p?
4s.
What do I fill about the 3p? 4s. So I just walk over and fill it. I will always know how to fill it. That was 18, 19, 20. How many more do I need? 1, 2, 3, 4, 5, and
6.
6. We good? The word for energy levels that have the same energy is degenerate. That doesn't mean an energy level of poor moral standing or anything. It's just the way, it's just the word that means same energy, I swear to God. These are 3 degenerate orbitals. What are the exceptions? What are the exceptions to the alpha principle? Copper, molybdenum, not tungsten. So chromium, sorry, I said copper. Chromium, molybdenum, not tungsten. Chromium, molybdenum, copper, silver, and gold. These 5. 1, 2, 3, 4, 5. And what is the exception? What is the exception to alpha? That instead of filling the 4s completely, you just put 1 electron in there and keep counting. We'll do it on Monday. The exceptions we'll do them on Monday. Between now and Monday, practice all your energy, frequency, and wavelength.